so now we're going to talk about some quantitative aspects of the kinetic molecular theory. We were introduced to this theory earlier, but briefly, I just basically quickly went through it. We're going to look at it in more detail. So what you see here listed are the principal assumptions of the kinetic molecular theory. The first one is that a gas is made up of molecules that are in constant random straight line motion. If you get a sample of gas in a container, most of it is basically empty space because the molecules are on average far apart from each other. There are no forces of attraction that exist between the molecules excepting when they collide. And then the last one listed here is that individual molecules may gain or lose energy as a result of collisions. However, the total energy remains constant. And the term that is used in physics in relation to the last statement here, the last assumption, is that the collisions are elastic. Basically what that means is that you have direct transfer of energy from one molecule to another upon collision. There's no lost energy elsewhere, so therefore the total energy of a collection of molecules will be constant as a result. Now, based on these principal assumptions, one can derive this equation right here. Now, let me just say that you don't need to know this equation, but you need to understand what this is saying. This equation relates the pressure of a gas to the number of molecules and the volume and the mass of the gas molecules, and this important term, which is known as the average of the squares of the speeds of the molecules. So what that means basically is that, I'm going to make a note here, is that the average of the squares of the molecules, the speeds of the molecules, will be equal to the square of the speed of gas molecule 1 plus the square of the speed of gas molecule 2 plus the square of the speed of gas molecule 3 plus all the way to the nth molecule, the square of the speed of gas molecule n, and then we divide all of that by the total number of molecules, which is n. So therefore, all of this here, all of this here is basically what goes into this part of the equation right here. All right? So basically, that's the relationship between pressure and all the other terms. Now, let me just highlight a couple of things coming directly from this relationship. Let me go back to my pointer. Okay, so first thing you'll notice here is that the pressure of a gas is inversely proportional to the volume based on this equation. So therefore, this is basically a confirmation of Boyle's law. Remember, Boyle's law says that the pressure of a gas is inversely proportional to the volume. Another relationship is that the pressure is directly proportional to the number of molecules. So basically, as the number of molecules increases, the pressure increases for the gas. Then we have the relationship between pressure and the mass of each molecule, right? And again, that's a direct relationship. The pressure is directly related to the mass of the molecule. So therefore, the heavier molecule will exert the greater pressure, everything else being the same. And then finally, the pressure is directly related to the mean of the squares of the molecules. In other words, this term right here, all right? So basically what that means is that if the molecules are moving at a faster speed on average, then that would result in a greater pressure exerted by the gas, all right? So therefore, that's basically what this equation is telling you. Now, based on this equation, one can derive, and I won't show you how to do that, but one can derive this equation here, which relates the kinetic energy to the temperature of the gas expressed in Kelvin. So as you can see here, the kinetic energy EK is equal to 3/2 times R, which is the molar gas constant, divided by Na, which is Avogadro's number, times T. So one can see clearly that this part here, let me circle it, this part here is basically a collection of constants, right? So we can replace that with basically a constant right here, all right? So therefore, we can say that the kinetic energy, average kinetic energy that is equal to a constant times the temperature in Kelvin. So what this tells you is that the average kinetic energy of the molecules is directly proportional to the temperature expressed in Kelvin, all right? So that's basically it as far as a quantitative description of the kinetic molecular theory. Okay, so I'm going to stop here, and in next video we'll be dealing with molecular speeds. All right, until next time.